Every computer science student has seen these two words in their syllabus: paging and segmentation. You memorize the definitions, you draw a diagram in the exam, and you get marks. And then you forget everything. But here is the truth: hackers don't forget memory. Most real world attacks don't start with hacking tools, they start with understanding how memory works. In this video, I'll explain paging versus segmentation, slowly, clearly, with real examples, and finally, from a cybersecurity and attack perspective. If you're a CS student, this video might change how you see operating systems forever. Let's begin with the core problem. Your program believes it owns the entire memory, but in reality, many programs are running together. The operating system needs memory, hardware has limited RAM. So the operating system has three big responsibilities: allocation, protection, and isolation. Allocation is who gets memory, protection is who can access what, and isolation is one program should not affect the other. If isolation fails, one program can overwrite another, and that is where vulnerabilities are born. Paging and segmentation are solutions to this exact problem. Let's talk about paging first. Paging divides memory into fixed size blocks. Logical memory is divided into pages, and physical memory is divided into frames. Each page is the same size, and each frame is the same size. This is important because when memory blocks are fixed size, the operating system doesn't care where they are physically stored. A program's pages can be scattered, non-contiguous, and anywhere in RAM. The operating system keeps track using a page table. Paging exists to solve external fragmentation. Memory is used efficiently, no wasted gaps, and there is a clean allocation. Imagine a book split into equal sized pages. The pages are stored randomly on shelves. You don't care where page 5 is, as long as you can find it. The page table is your index, and that's paging. Now, segmentation. Segmentation divides memory based on logical meaning. Instead of fixed sizes, memory is split into code, data, stack, heap. Each segment has a base address and a limit. This feels natural to programmers because this is how we think about programs. But segmentation has a cost. Segments are variable sized. They must be stored contiguously. Over time, memory becomes fragmented, and that's external fragmentation again. Let's pause and compare paging and segmentation. Paging has a fixed size, it is operating system controlled, it's hardware friendly, and better isolation. Whereas segmentation has a variable size, programmer friendly, it has logical structure, and fragmentation risk. This is why modern systems use segmentation and paging combined. Now comes the part that textbooks don't emphasize. Many cyber attacks are memory attacks: buffer overflows, stack smashing, and privilege escalation. These attacks work by crossing memory boundaries, ignoring limits, overriding adjacent memory. Segmentation tries to enforce logical boundaries, and paging tries to enforce isolation. When memory protection fails, attackers gain control. This is why understanding operating system memory makes you a better security engineer. For exams, remember this: paging equals to fixed size, which is equal to no fragmentation, and segmentation equals to logical, which equals to fragmentation possible. But for real life, memory management is not theory, and memory management is security. If you're a CS student who wants concepts explained clearly, real world connections, and cybersecurity foundations, then this channel is for you. Subscribe because we don't memorize, we understand.